Good afternoon, everyone. Welcome to the H+C webinar. The title of the webinar is Cooling in Indian Homes. I'm Dr. Andy Smallbone. I'm an associate professor at Durham, and I'm the Network Plus lead. This event is organised through the EPSRC Network Plus for the decarbonisation of heating and cooling, and is part of a series looking at different challenges of decarbonising our heating and cooling sector and behaviour. This month, we're delighted to welcome two speakers from Heriot-Watt University to talk about the research in assessing energy demand reduction and decarbonisation of cooling in India. We're really grateful to both presenters for providing their time. So the first person to speak is Professor David Jenkins. He is a professor of energy and buildings, and he's leading the Urban Energy Research Group at Heriot-Watt. He's an active researcher since 2005 and has over 100 publications in the field of energy, buildings, and has worked on a number of research projects such as Tarbase, low carbon futures, adaptation and resilience in energy systems, community scale energy demand reduction in India, Reflex Orkney, and the Centre for Energy Systems Integration. He's also a co-I for this network. So David, please.
Thanks, Andy, and good afternoon, everyone. Hopefully you can see and hear everything you need to. I led this project, CEDRI, Community Scale Energy Demand Reduction in India, alongside colleagues in Heriot-Watt and also IIT Delhi, IIT Bombay, and NIT Trichy in India. So we're going to focus a little bit on the focus on cooling load in this project, and how to reduce and manage cooling load in some of the communities in India that we were looking at. So it's a 4-year project funded by EPSRC's Newton Baba scheme, alongside 3 other projects looking at sort of similar issues within sort of energy use in Indian buildings and communities. And our starting point is really to try to design energy demand reduction strategies in India. But for our case in particular, looking at three sort of disciplinary areas, trying to understand the evolution of the built environment, first of all, so what's happening to buildings in India, and in particular the cooling use of those buildings. Local network constraints, so trying to sort of pick up on some of the changes that are happening in the local energy systems that are supplying energy to those buildings, particularly around electricity usage. And then also, rather than just kind of putting a full stop on the buildings and the engineering, trying to interact more with the actual householders themselves, the people using energy in those buildings, and having various kind of co-production exercises to learn from how energy is used in those buildings, and the sort of cultural impacts and the sort of technological impacts that might change how we think about cooling. So amongst all the many challenges of trying to understand energy demand in India, what is a typical building is probably the first one. I mean, anyone who studies energy use in buildings will know that referring to a typical building to describe the entire country is a bit of a fool's errand anyway, but it's even more so probably in a country as diverse as India. So in terms of the case studies that we were looking at, I mean, we had blocks of sort of apartment blocks that people might be quite familiar with, regardless of what country you're from. I can't say we did a model of this particular building, but this is a temple in the middle of one of the communities that we were looking at in Auroville, which I'll mention a little bit later on, just to give you an idea of how untypical some of these case studies might actually be. But of course, if you're thinking about urban development in the sort of larger Indian cities, you might think of something a bit more like the bottom picture there, where you've got high density buildings, a mix of formal and informal settlements, and quite a broad mix of HVAC systems and approaches towards cooling, ranging from no technology at all to having integrated mechanical cooling units in those buildings. So diversity is the first challenge, which is perhaps an unsurprising one. But also because we're quite a forward-looking project, we want to think about where energy is going in the future in some of the communities that we're looking at. And of course, the solutions themselves, we're perceiving would happen at some point in the future. You have to try to understand the change that's already going on in India. So India is predicted to be the largest country by population in a few years, according to some UN projections. So in the next 5 years, it's predicted to overtake China. That's obviously going to have an impact on energy use, but also within that population growth, there's an assumption that there'll be a growth of middle class households with disposable income to spend on things like mechanical cooling. So you'll have this kind of cultural shift where people can afford things like mechanical cooling units, but also it will be expected to have those mechanical cooling units. I'll mention a little bit later on the current penetration of cooling systems in India, but it's relatively low penetration point of cooling systems in residential buildings in India compared to somewhere like China, where it's a bit more common. So that means the scale of change is likely to be higher. So that's something we need to think about. Obviously, climate change affects India just like it affects any other country, arguably more so in some of the communities that we were looking at. So how is that going to impact cooling loads? And then just looking at energy demand more generally, this is one projection from the IEA in terms of the size of the energy demand in billion tons of oil equivalent, but also where that energy demand might come from, obviously the carbon implication of that as well. So it does leave you with this picture of sort of inevitable rise of electrical cooling demand in that country. So that's your kind of starting point, and we can't ignore those kind of external parameters, that external change. So what we were trying to do as a project was bring together essentially three disciplinary areas. So network modeling, so trying to understand local network characteristics, the networks that are serving some of these communities, how those grids are going to evolve in the near future based on conversations that we had with industrial partners in India, and understanding the resilience of those networks to future change. And obviously have to define what that future change actually is based on the views of people actually working in those industries. And then on the building demand modeling, there's sort of two parts of that. One was looking at monitored energy demand data that we had from our case study communities, trying to take a sort of statistical approach to empirical energy demand and understand the signals from that data. And then also carrying out physical modeling to test out different demand reduction measures to alleviate some of the likely rise in cooling loads in some of these buildings. And finally, on energy behaviors, we ran a series of surveys, questionnaires, co-production workshops with the communities that we were working with, that we were studying, and trying to feed from them what not just their baseline energy behavior is, so the drivers behind their current energy use and why perhaps certain cooling patterns might be seen or not seen, but also then trying to understand for different futures what technologies, what systems, what processes might be well received or not well received, and rather than just dumping some kind of future scenario on that community saying this will be the case, trying to listen to them as to what futures they perceive within their communities in the coming decades. So I'll talk about those in a little bit. Anyone approaching this type of project might be familiar with the idea. If you have several different disciplines at the same time, several different modeling families or assessment families, if you like, there's this temptation to somehow meld all these different approaches together to create some kind of mothership of a modeling process, so hardwired model that does all things to all people for those buildings and for that wider energy system. And what tends to happen as you get further into this type of project is you realize actually that's not necessarily the way to go. You've got different questions that you want to ask, what we would refer to as a toolkit of models. That toolkit of models, it doesn't have to be a single entity of this kind of super integrated energy model. But what you're essentially doing is, if you look at this flow diagram, which is actually a tidied up version of what we actually did. On the left of the diagram in green are typical inputs that you might try to gather from a case study community. In far right, you've got findings or conclusions or applications that you might be trying to look at, so questions that you're trying to answer. In this case, impact of demand reduction on individual buildings, or impact of demand reduction on the network, where you're looking at aggregated energy use of buildings, and all the other questions that come under that. So you're kind of dipping into different processes, different models, depending on the questions that you're trying to ask, and you're trying to answer. But it's not necessarily the case that you need to run through all those different tools just because you have them to answer that question. So it's a bit of a kind of sort of pick and mix approach, but understanding that toolkit does have some commonality in terms of the inputs it uses, the external scenarios that it might use, the external parameters. So there is a consistency there. It's just not necessarily a single model that you're asking the same questions to. You pick and choose out of that toolkit. What models do I need to find out the things that I need to find out? So in terms of the case study itself, Auroville we had a couple of case studies, but Auroville was the one that we studied most closely. There's a model in the top right of this slide showing you the kind of setup of this community. Again, very much not a copy and paste community that you necessarily see across the whole of India. A sustainable community in Tamil Nadu, an intentional community. So these are people that have gathered in this community, Indian, non-Indian, so quite a mix of residents, with a strong sustainability ethos across that community in everything they do, which is actually quite an interesting thing to have for some of our social science work that we did in CEDRI. So within that community, we're trying to carry out a number of modeling tasks, including synthesizing demand profiles from the monitored data. So we have all this data from monitored households in that community, but we want to be able to synthesize new profiles from that data. Physical modeling to test out demand reduction solutions for certain chosen buildings within that community to see what can you do with the buildings themselves to try and alleviate some of the problem of peak cooling loads. Understanding the local drivers of energy behavior, and local is really the key word there. So we're not, again, copy and pasting these findings, these local drivers to every community in India, but there's a process we go through to try to understand those local drivers, and we think that process is the thing that's replicable to other communities. But also to understand, as I said before, not just the baseline, but the future change. And then from all that, trying to understand the potential energy demand scenarios that might exist for this community and other communities in the coming decades, and what we can do with our modeling toolkit to respond to some of those challenges. On the demand synthesis, first of all, which was led by my colleague Sanjay Patidar, all this work is published, so for anybody wanting more detail on the processes, please do get in touch. But the idea behind here is that you can take an observed demand profile, such as the one in the top graph of this slide, and split that into constituent signals. So you can imagine in a profile of that type, you've essentially got lots of different characteristics, lots of different signals that are occurring at different periodicities and different scales and magnitudes. If you can filter them out, then you can start to look at whether certain signals have certain correlations with external parameters such as weather. So if this was a UK profile, you wouldn't expect any spikes to do with boiling a kettle necessarily to have a strong correlation with external temperature, but you would expect, for example, an electrical heating system to have a very strong correlation with external temperature. So by filtering out different signals from that profile, not only can you remodel synthesized profiles, such as the one in the bottom of the slide, but you can also then morph those profiles for some future scenarios if you have evidence of a correlation between one of those signals and some of that external data, such as external temperature, external weather variables, but also things like occupancy data and that kind of thing. So we were able to synthesize these demand profiles, essentially taking data from 30 houses and synthesizing them into data for maybe 100 houses, assuming you've got your weightings and your approach correct. But then also, as I say, morph for future scenarios so that we can start to test out what the demand might look like for some of the future scenarios that we were working with. And then, so this is an example, first of all, of what that looks like when you aggregate. And this is something like 200 houses together. In black, you can see the baseline demand profile. This is over the period of a couple of months. You can see the daily cycles for this aggregated demand. But then you can also see in blue the morphed signal for a future climate file, a future climate scenario that we were using, because we have that correlation between external temperature, external weather variables, and demand, particularly cooling demand. And we can do things within that aggregation. We can change, for example, the frequency or the penetration of cooling systems, because you wouldn't have started off with 100% penetration of cooling systems in these dwellings. Many dwellings didn't have any cooling systems. So you can play about with all these different parameters to see what happens to that aggregated demand. And then you can take that and bring it into some of the network modeling that we were doing. So this was carried out by one of our researchers, Benoit Courreau. So you can take a fairly standard network model and then populate the nodes of that network model with our synthesized data, with as many dwellings as you want. You can change the definitions of those dwellings, put in a cooling system, run a cooling system in a certain way. So we could specify all the houses in that network model. We could specify what they're doing within certain limitations of information we have for both a baseline and a future scenario, and then see how that network model copes in terms of frequency and voltage characteristics. And also thinking about things like, well, what happens if you put a high penetration of solar PV into that network model? Can we do a series of things that potentially causes a problem in that network model, and how would you alleviate that problem? So Benoit has published a couple of papers on that as well. And then moving on to some of the dynamic building simulation work carried out by Kumar Devnath at Heriot-Watt. So we just wanted to model some of the actual apartment blocks physically, and then run different fabric solutions to try and see what happens with the temperature profile of those buildings when we play about with thermal mass and insulation levels. But also how that impacts a naturally ventilated building compared to an air-conditioned building in terms of the demand profile that ends up coming out. Kumar also carried out a study looking at heat stress indicators. So how does that change when you compare a baseline with a sort of future version of that building in a future climate, and so on. And we can inform that by some of the activities from the monitored demand data, because obviously if you have measured electricity consumption data, you can use that to generate activity schedules, because it tells you something, just looking at the spikes and the features of that demand profile, it tells you something about the occupancy of that building over time. And we also had behavioral information from engagement with those households. So we know what appliances they have, but also how they interact with those appliances based on the reported evidence that we were given. On to that sort of behavioral aspect. So we ran 20 in-depth interviews, and this work was led by Olu Osunmuyiwa at Heriot-Watt University. So started off with 20 in-depth interviews with householders to understand cooling preferences, and just a bit more generally their engagement with energy. So there was a series of questions that tried to kind of set a baseline of how the households interact with energy, but particularly cooling. And then a wider questionnaire was sent around that community, informed by the responses of the interviews, trying to identify what a typical household actually is within that community, what existing energy saving behavior could be pointed to. And bear in mind, this is a sustainable community. That was quite an interesting exercise, because there's this feeling, as much as anything else, that cooling is bad. Mechanical cooling is not something you do in a sustainable community. That historically was quite an sort of entrenched view for understandable reasons. But also asking questions around things like time of use tariffs as we look to the future. What sort of solutions might be viewed favorably by this type of community, and what are the barriers to those changes? So we ran two co-production workshops. The first one was on with the householders themselves, looking at cooling flexibility options and what might a local policy of dealing with cooling actually look like. And then a practitioner-focused workshop, which was a separate exercise, trying to ascertain what the challenges to local energy networks would be. So we had a number of industry partners from India speaking to us about their recent experiences and how they perceive the future to be within their industry, and then trying to understand the role of projects like CEDRI in helping inform that change. And just sort of some kind of quick conclusions on that piece of work. I mean, there was clearly a diverse range of values impacting cooling behavior from this community, ranging from biospheric, altruistic, economic, cultural, although this was a specific community, you can see some parallels with behavior sort of outside that community as well. But just the process of trying to pick up the drivers themselves was an interesting exercise. But it makes identifying triggers for cooling a bit more complex, because it's not just about simple temperature set points. I mean, as building modelers, we like to have a clear number of 23 degrees, people turn the cooling system on. But of course, it's not anything like as simple as that. So it's also about this kind of perception of temperature within a context of warming climate, and also health implications of being too warm. What was particularly interesting for this community, having said that they viewed mechanical cooling quite sort of suspiciously, if you like, because of the energy and carbon implications for a sustainable community, they were also very aware of warming temperatures. And then for some householders, particularly more elderly householders, they were being told by their GPs, look, if you allow yourself to get too warm, particularly with climate change going on, this is going to have a detrimental effect on your health. You need to do something about it. And so people were becoming far more open about using cooling systems within this community because of this change of information and change of context. And even though this was quite a specific change to Arraville, this as a sustainable community of we don't use cooling, and that kind of almost local cultural shift, there's a strong parallel as well with other communities in India, because other dwellings in India don't use cooling as a norm. I mean, only about 12% of Indian homes currently have air conditioning. And for the reasons I said earlier, for mostly economic and social reasons, we'd expect that figure to rise quite dramatically to maybe match countries like sort of China over the next couple of decades. So there is this process of change. In the case of Arraville, it's a change from a kind of sustainable approach to something that's a bit more aware of health implications. The rest of India or other communities in India might just be a purely economic one, that people can now afford cooling systems. And so again, you're expecting this steep gradient of change around the use of cooling. So that came across quite strongly. So as I say, all this is published. Very happy to talk about some of the specific findings, but just very generally, so general findings. We felt there's this need to match demand reduction strategies to specific communities with an understanding of future change. This idea of tailoring your solution came across quite strongly. We produced methods where demand synthesis can help link building demand scenarios with network models, so bridging the gap between, if you like, traditional building assessments with energy system and network models. Purchasing and energy behaviors of households are crucial for the success of these demand reduction strategies. Again, this need for tailoring, it's very easy to overgeneralize, whether it's a country as small as the UK or a country as large as India. But you have to understand the kind of nuances between different regions, different socio-demographics. And these strategies require modes of communication that involve the householders themselves. We're very guilty often as academics to come up with solutions that we apply to people rather than trying to work with people to understand how if those solutions are even possible or appropriate. In the case of India, the challenge is obviously to manage an inevitable rise in cooling-driven electricity demand, not to reduce it. And that's quite a difficult thing, quite a difficult starting point for a project like this. But our challenge is to reduce the demand from what it otherwise would be, rather than to reduce the demand from what it currently is.
Thanks, Dave. Thank you very much.